All right. So we are going to prove this result. Let me erase also this board. Bu daha önceden kalma değil mi? Evet. Oops. Okay, here is the proof. We already know that from last lecture, I guess, we had this equalities. Shape operator at V, cross product shape operator at W. This is just the Gaussian curvature and V cross W, right? And the second one, shape operator at V cross W plus V cross the shape operator is just 2 times the scalar curvature V cross W. And we used these actually to derive the formulas for Gaussian curvature and scalar curvature last week, right? The formulas were, you know, in terms of EGF and LMN, right? We used the same formulas, and we had used one more thing, Lagrange identity, which is about cross products. Okay, now by assumption, so we will again make use of these. By assumption of the lemma, we are trying to prove we have Z equals V cross W, right? So taking that product with the vector field Z, we get what? Let me tell you what we get. Now, this is Z, right? This is Z. So I take that product of this expression, both sides with Z. When I take that product with Z, I will get norm Z squared. And here I will get this expression, that product with Z. So we get what? And this becomes a scalar, right? This is a number. And we know that this number is not zero because this is a normal field. So nowhere zero, normal field, right? Non-vanishing normal field. Therefore, norm of Z is never zero. So this will be just that product of this expression with Z divided by norm Z squared. So we get kappa. P is just that product with Z of this expression. SV yes, cross SW divided by Z dot product with Z. All right. And note that we have also the following. Note that okay, SV cross SW is equal. All right, let me write that down. What's that equal? Okay, so that's equal to the following. So what is this? This is just minus the covariant derivative, right? Cross the covariant derivative of this. Yeah, here I am using the fact that, okay, maybe I should write this in more detail. Remember that SV is what? We computed this. This is covariant derivative of this, of Z. No, not Z, of U. U is the unit normal vector cross, right? Where U is the unit normal vector field. And we computed this. This is just minus the covariant derivative of Z divided by norm Z cross NV cross this expression. This is minus the covariant derivative of W, I'm sorry, Z divided by norm Z cross MW. All right. So when you open this up, you will get what? Let me tell you the result. So this cross vector cross this vector field, I have two minus signs, they will disappear, and this is just a scalar, so it will be just 1 over norm Z squared, and then the cross product of this cross with this one. So this is from the first term, and then I have this term cross this term, that's a minus 1 over Z norm, and then the covariant derivative of Z cross product and W, and then minus 1 over Z again. This time I have this times this guy, so NW cross the covariant derivative of Z plus NV cross NW. But I know that these two vectors are both parallel to the normal vector field. Therefore, these are parallel, and therefore this is 0, right? Because these two vectors are both normal to the same surface, so that they are parallel. And cross product of two parallel vectors is 0. So what we obtained is then this expression here, right? Kappa was Z dot product with this divided by norm Z squared, and I have computed this in terms of covariant derivatives and this normal vector fields. All right. So kappa P, which is just Z dot product SV cross SW divided by norm Z squared or Z cross Z dot product with Z is equal to what? So çok yaşa. I have to take dot product of this expression with Z. Okay. Well, this is a normal field. Cross product of this vector with any vector is perpendicular to the normal field, right? If you have two vectors, their cross product is normal to both of them. So this is normal to this guy. So it is normal to Z also, right? So if I take dot product of this with Z, this term will die. And similarly, this term will die. Okay? Because this is parallel to Z. Therefore, this cross product is perpendicular to Z. So if you take dot product with Z, this term will vanish and this term will vanish. So this will be the only surviving term. So as I said, this will be the only surviving term. So Z dot product covariant derivative of Z along V and cross covariant derivative of Z along W divided by, here I had already norm Z squared, and here I have another norm Z squared, so this is norm Z to the power 4. Yes, yeah, you're right. Okay, thank you. This is understood, right, why these terms vanishes. This is because, let me write it again, because the second and third terms are both perpendicular to Z. Okay, so that their dot products with Z will vanish. So we are done, I guess, right? So we obtained this formula, right? We obtained this formula. Okay. For Gaussian curvature. What about this one? Well, I mean, it will be basically the same thing. Okay, so I will not do that. So the second, the proof of the second statement about the scalar curvature HP can be proved similarly. And I leave it as an exercise. Okay. So you will just repeat the same arguments, maybe in different order. Okay. What else? All right, let's see one example. Okay, so let M be the ellipsoid defined by G x1 squared a1 squared plus x2 squared a2 squared plus x3 squared a3 squared minus 1 equals 0. So G is this expression, this function of three variables, equals 0 gives my ellipsoid. What is the gradient of G? Gradient of G is just 2x1, right, divided by a1 squared, 2x2 divided by 2a2, no, just a2 squared, and 2x3 divided by a3 squared. And this is never the zero vector, right? This is never the zero vector on M. Why is that? Because on M, the sum of these three terms is equal to 1. Therefore, x1, x2, x3 cannot be 0 simultaneous, right? At least one of them is not 0. Therefore, this vector is never 0. So this is a 0 is a regular value, and M is a surface, and Z, which is just gradient of G, is a normal field on M. All right. Okay. Somehow the author took this one. Well, gradient of G is a normal field. It's, if you divide it by 2, it's again a normal field. Why do we do this? Because, I have this 2's, so you get rid of that 2's, okay? Z, remember, doesn't have to be a unit normal vector field. It's just a normal vector field. So any multiple of this, any non-zero function multiple of this is good. And to make the computation easier, we just divide it by 2 so that we get rid of this extra 2's. Now, Z is then equal to what? I can write this vector field as xi divided by ai squared times ui, right? I from 1 up to 3. So I write this vector field in coordinates, half of it in coordinates. So x1 divided by a1 squared times u1, x2 divided by a2 squared times u2, and plus x3 divided by a3 squared times u3. u1, u3, u1, u2, u3 are the standard orthonormal vector fields, right? So u1 is this 1, 0, 0 at any point, 0, 1, 0, and u3 is 0, 0, 1. At any point, these are the vectors given by So they are constant vector fields. Okay. Now, to compute the Gaussian curvature and scalar curvature, all I need is Z, right? So all I need is Z and two vector fields whose cross product is Z. Okay, normal vector fields whose cross product is Z. All right, let's see how we can do that. Let Vi times Ui be a tangent I from 1 to 3, of course, be a tangent vector field on M. Then the covariant derivative of Z, sorry, along V is what? Z is this expression. Z is this expression. What is the covariant derivative of this? It will be just the covariant derivative of functions xi divided by ai squared times ui, right? Actually, I have another term here, right? I have another term. What is that? That function times
Yıldır hocam
covariant.
pardon. Sanırım kamera kaydı dondu fakat.
Evet.
Teşekkürler hocam.
Rica ederim. Okay, so Z is this expression, right? Z is this expression. When you take covariant derivative, you take derivative of this times ui plus this guy times derivative of this. But this is a constant vector field. So the covariant derivative of this is 0, okay? Therefore, I have this expression here, but that is just 0. Therefore, I have only this term, okay? And what is this? V computed on this vector, and V is just Vi times Ui. So I'll just take derivative of this in with respect to first coordinate, second coordinate, third coordinate, and then yes. So okay. Now, what is this gadget? V of xi ai squared. Well, this is a constant. I can just take it outside. V of xi, but V is this vector field. So what is the derivative of, I may maybe write this using another parameter j. So this will be just 1 over ai squared. And then j from 1 to 3, vj uj evaluated on xi. So what is this? You just take derivative of this with respect to j. So this is just del xi del xj. But that is either 0 or 1, right? It is 1 if j equals I. So I will just get 3 terms here, 0, 0, 1, right? One of them will be 1, the other will be the others will be 0. So I just have 1 over AI squared. Yani bu x, i'nin türevlerini alıyorum değişkenlere göre. i'den farklı değişkene göre türevleri 0, i'ye geldiğimde 1 verecek. Dolayısıyla bu toplam this is just 1. Okay? This is just 1. I mean, I have also, of course, this vi. This is 1. So this thing is 1. And then I have vi. So what we have is then covariant derivative of this is just I from 1 to 3 vi divided by ai squared times ui. Right? I have computed this times ui. This gadget is just vi divided by ai squared times ui. All right. What else? Okay. Let me erase this part. Similarly, of course, if W is just this Wj, Uj, J from 1 to 3, then covariant derivative of Z with respect to W will be the same expression, right? I from 1 to 3, but this time I will have Wi divided by AI squared times Ui. Bu gene donmuş. Özür dilerim. Okay, so I just wrote this thing for the vector field V. We had computed this. If I change this vector field to W, then of course I will get this expression. Okay. Now, we have this. Now, Z dot product, the cross product of this expressions, right? For the Gaussian curvature, I need this expression. What will be this? We take cross product of two vectors and take the dot product with the resulting vector. How can we do this? I write this as the first row, this one is the second, and this one is the third row of a matrix, and then we take the determinant. Z has coordinates x1 divided by a1 squared, x2 divided by a2 squared, and x3 divided by a3 squared. This vector was, so the coordinates of this one, v1 divided by a1 squared, v2 divided by a2 squared, and v3 divided by a3 squared, right? So let me just, the coordinates of this vector are just these numbers. So let me write that down. A1 squared, V2, A2 squared, V3, A3 squared, and then W1, A1 squared, W2, A2 squared, and W3, A3 squared. And if you do the computation, let me tell you what you will get. Okay, I take A1s out, A1 squared out. From the second column, I can take A2s out, and from the third one, I can take this one out. And what is left? I have x1, x2, x3. That is just, okay, let me write it. That one is x dot product v cross w, where x is this vector field, x1, x2, x3. Okay, and v was the vector v1, v2, v3, and w was the vector w1, w2, w3, right? So we have this expression. And note that, okay, if v and w are chosen so that their cross product is z, then what will be this expression? Then x cross x dot product v w will be just x times z. Okay. Remember, to make our computations, we need these vector fields so that their product was the normal vector field z. And if you do so, then this expression will be just x dot product z. And what is x dot product z? X is this vector field, z is this vector field. So you take dot product of this and this one. So it will be x1 squared divided by a1 squared, x2 squared divided by a2 squared, x3 squared divided by a3 squared. So this will be just x1 squared over a1 squared, x2 squared over a2 squared, x3 squared over a3 squared. And what is this? On the surface, this is always 1. Okay. So before actually we, I didn't explicitly choose this vector fields at all, but we know that they can be chosen. And once you do that, I mean, actually you don't have to even choose them explicitly, but once you know that what they are, implicitly, you can compute this expression. So this is, so what is the Gaussian curvature then? Okay, let me, yeah, no. Let me erase the board. So the Gaussian curvature, what is the Gaussian curvature? This expression, which we just computed, divided by norm z squared. So Gaussian curvature, which is just z dot product with this. We computed the numerator. That is just 1 over, right? So this is just 1 over a1 squared, a2 squared, a3 squared. Let me, right? this expression is equal to this scalar times this expression, and we computed that this is equal to 1. Therefore, this expression is just 1 over this gadgets. Onu göstermemiş. Okay, yeah, let me repeat. Right, we computed this. It is this scalar times this scalar, and this scalar is just computed to be 1. Therefore, this expression is just 1 over a1 squared, a2 squared, and a3 squared. And now I take that one and put it here. So okay, 1 over a1 squared, a2 squared, a3 squared, and norm z squared. Where what is norm z? Norm z to the power 4. Z was where was z? Yeah, z was this vector field. Z was this. So what is the norm of this? You just square these coefficients, add them up, and then take the square root. I have 4th power. Therefore, I will have this expression squared, summed up, and then I need to take square of that thing also. Where norm z to the power 4 is just, okay, xi squared ai to the power 4, right? I from 1 up to 3. If you take square root of this, you get norm z. But I need 4th power of z, norm z. So I need to take, okay, square of this. Okay. So whatever, you know, this is yeah. If A1 equals A2 equals A3 equals R, then this is a sphere of radius 1, right? No, radius 1 over R. Maybe I should say 1 over R, let me say. Then so x1 squared yok. No, it should be R. R squared x2 squared R squared x3 squared R squared 1 is the sphere of radius
Yıldır
R.
hocam pardon. Kamera sanırım orta tahtayı şu anda çekiyor ama.
Tamam, özür dilerim.
Teşekkürler.
Okay, so Gaussian curvature was this. We had computed this expression. It was this expression. And then I have 1 over z to the power 4. Norm z was this expression, square root of this expression. Therefore, 4th power of this will be just square of this gadget. And here we do the special case. If A1, A2, A3 are the same, and if they equal to R, then this becomes nothing but the sphere of radius R. And in that case, Gaussian curvature would be what? We know what this is actually, right? So that would be okay. Now these are both r's, so I have 1 over r to the power 6, and then here these are also r to the power 4, and then I have squares of xi's. Sum of squares of xi's is just r squared. So this is just r squared divided by r to the power 4, which is 1 over r squared. And then you take square of this, so this becomes r to the power 4. And you divide this expression with this, 1 over r to the 4, so we get 1 over r squared. So the Gaussian curvature of a sphere of radius r is 1 over r squared. Of course, that is not a surprise. Why is that? We already computed that the normal curvature on the sphere of radius r along any direction was 1 over r squared, or minus 1 over r squared, depending on whether you choose inward normal or outward normal. But since the normal curvatures are constant, the shape operator is basically the identity operator times a scalar, and that scalar is 1 over r squared or minus 1 over r squared. So the shape operator for the sphere is this: plus or minus 1 over r squared, 0, 0, plus or minus 1 over r squared. Identity operator times 1 over r squared or minus 1 over r squared. So what is the determinant of this? 1 over r to the power 4. Okay, so it should be 1 over r squared. Neyi yanlış yapıyoruz? Gaussian curvature is determinant of the shape operator. Oh, sorry. For any circle of radius r, its curvature is 1 over r. Yes, not 1 over r squared, right? If you have a circle of radius r, its curvature is 1 over r, right? Curvature. So if this is 1 over r, therefore these are 1 over r's. Determinant is 1 over r squared. Sorry. In this case, these circles are which circles? You have the sphere of radius r. Whenever you have a point and a direction, you consider a plane which contains this point, this vector, and the vector, the normal vector to the surface. So that plane is the plane which contains this point, the origin, and this vector. So this means you cut this sphere with a plane passing through the origin. What you get is a great circle, a circle of radius r, the radius of the sphere. And for that circle, curvatures are always 1 over r. Along any direction. Therefore, the shape operator is 1 over r times the identity operator, and therefore its determinant is 1 over r squared. And this is insensitive to the choice of the normal vector, unit normal vector. Either way, going upward, downward, inside, outside, doesn't matter. You get the same result. Okay. You can also compute scalar curvature, of course. All right, I think we may stop at this point. As I said, you should know the formulas, how to use them, but if you cannot memorize them, it doesn't matter. I will give them to you. Just work on the problems assigned for each section. That's the best way to understand whether you are ready for the exam or not. All right, let me stop.